Hello and welcome to Deep Linux. In this video, I'll be talking about different heap arenas. Now, previously, I always mentioned that we're going to have a main arena that is allocated via sbreak. So if this is the memory space of a process, let's say this would be the data part, and this would be the code, and this is how the address kind of this is larger addresses. Okay, and then here we're going to have the stack. So what happens is that you probably know that the stack kind of grows backwards towards lower addresses, and then the heap, which is here, grows towards larger addresses. Now, this heap that we're showing here is basically the main arena. You remember that we had a pointer by this name, a struct by this name, and this is the main part of the heap that is allocated and then extended by basically running the sbreak system call. So this sbreak system call kind of breaks the bottom of where the data ends and kind of pushes the heap down as we move forward. So as we need more and more heap memory. Now, sometimes we would need to use more of these so-called main arenas. But in that case, we're not going to call them main arenas. We're just going to call them arenas. Now, why? Okay, let's say we had two threads of execution. So there is one thread, thread 1. You know, it's doing a malloc. Let's say it's allocating a block of memory here, right? What that means is that thread is going to be changing some memory around this area. You know, it has to, basically the glibc library is going to be responsible for doing this, but what it's going to do is that it's going to, you know, put the metadata of the thread of the block of memory. But before that, it's going to find a place to first off carve the block out of that area which is free. It's going to look into the small bin, it's going to look into the large bin, maybe fast bin, so on and so forth. So there's a lot of things that it has to do, and then it's going to change the state of the heap. That's all fine, right? But what if we had a second thread? So we had this second thread which is also running, and it wants to allocate heap. So if they turn out to do this at the same time, we can end up in a race condition. A race condition is basically when two threads race each other to change some data, and the same data basically. So the heap state is here, the data. It's not just the heap state, but the heap itself, right? So one could go and allocate a block of memory, and then in the middle, the other thread could come, and then heap is in an intermediate incomplete state, so it could allocate the same block of memory, which has been partly allocated but not finalized. So things can get messed up, and we end up in this race condition, heap corruption, and whatnot. Now, to prevent that, we're going to use a lock. And you all probably know what a lock is. Or sometimes by the name of mutex. What happens is that here, if you take a look at this piece of code here, glibc malloc, this is where the malloc actually happens. This is the internal C function that's called. This is actually an alias of malloc that you call. Inside glibc, it's called glibc malloc. And at this point, if it's not single thread, it would do an arena get. But what is arena get? Let's go there. There's this also important C file called arena.c. And here you see that we're getting a arena lock. And what arena lock is that it locks a mutex, which is part of the data structure of that arena. You remember the mutex that we had? Here, GDB. I'm going to say heap small bin and p main. Oh, actually, I need to run it. Put a breakpoint and then run. Now, main arena. You see there's a mutex here. Well, I haven't allocated anything, so the arena is basically empty. Okay. So this mutex here is what I'm talking about. This is the same mutex that you see here, right? It ends up pointing to this guy. So it has to acquire that lock to be able to do the things that it wants to do, because if another thread comes and then sees that lock, which is held on to, it's in locked state, it's going to withhold and wait, or basically block, until the mutex is released. And then this is going to prevent any sort of race condition and heap corruption. Okay, so let's go back here. Okay, so we need a lock, right? But then if we need a lock, then this lock contention is gonna waste a lot of time. Now, every time this mutex lock is taken, right? Every time that this is taken, this is a system call. And the system call is usually called futex. At least in the system that I have, this is going to map to the futex system call. Okay, and this is well, relatively heavy compared to just doing a malloc, right? Without having to require a lock. So we're actually incurring a lot of overhead by having different threads share the same main arena. Now, the idea here is that when we have a multi-threaded application, instead of having only a main arena, we're going to create a bunch of other arenas, which is going to look like this. So if this is the virtual address space of that process, and this part is the code, this will be the data. This is going to be, let's say, the main arena. I'm just going to call it the main arena, which is the main heap. And it's going to be extended using break or sbreak system call. Right, forget about the stack for now. What I'm going to do is, as more threads come or are created, I will create arenas, independent arenas. So I'm just going to say arena 1. I'm going to create another one, which is arena 2. And obviously I'm going to leave a little bit of space here so that it allows my main arena to grow. Now these other arenas, they are created via mmap, which is another system call. But the thing about mmap is that you specify the size of the memory that you want right up front. So if we go here in the where malloc is done, actually, I'm just gonna search for mmap. Okay, so this is a function where we actually create a new heap or a new arena. Whenever we say heap or arena, we mean the same thing. Okay. So whenever we want to create one of these new arenas, we're going to be calling new heap. And it's just going to, create it for us using the mmap. There you go. This is where it's called. This is a macro that's expanded to mmap, right? So this is where it calls the mmap and it kind of creates this arena and then that arena, so on and so forth. Okay. So this is how this whole thing happens. Now, so trying to say is that arenas are created via mmap, whereas the main arena is created via sbreak or extended via sbreak. So an arena is created once and then the size doesn't change, right? That's the size. The other thing is that every arena is assigned to a thread. So the idea is that, the best case scenario for us is to assign one arena to every thread. So there is this variable that determines how many arenas we create. Okay, and it's called ncore. So ncore, n arenas from ncore. I'm just going to go to the macro here. You can see that it's defined as, this is basically telling us that from n cores, let's say you have n cores, how many arenas you want to have. This is the number of cores times either 2 or 8, depending on the size of long. So this is basically what this means is that in 32-bit systems, the size of long is 4. So you're going to have 2 times the number of cores, arenas. Okay, so let's say my system is 16 core. If it were 32-bit, I would have 32 arenas max. Okay, now my system is 64-bit and 16 cores, so the size of long is going to be actually 8, which means that this part of this expression is going to be true, is going to be evaluated. So 8 times 16 means I'm going to have how many arenas? 128 arenas max for 16 cores, which is a lot, right? There's no way I'm going to have 128 threads. Okay. Now, there are glibc tunables that you can use to actually change this. And there's another parameter, it's called arena test. So this arena test actually overrides the other one. And let's say you just want to enforce a certain value on the number of arenas. Let's say, okay, forget about the number of cores I have. I don't want to have more than 5 arenas. You just set this to 5 and that's it. And I'll show you in an example how to use glibc tunables to actually play around with these. Okay? Because sometimes you don't need a lot of arenas, because using more and more arenas means that you're going to increase the size of the heap, because you're going to be doing these mmaps of let's say every time it's going to be around, I believe, 16 megabytes at minimum. So every time you allocate an arena in a 64-bit system, I believe it's around 16 megabytes. Okay, and sometimes you just don't want to have this. Well, obviously you're not going to get all the arenas if you don't have that many threads, but maybe you have so many threads, but those threads are not really that much using the heap, so you don't really care for them to acquire the lock once in a while. So you can actually have these parameters to play with. Okay, so there are some downsides to this as well that we have to be aware of. And let's say we can do an analysis and see what is the resident memory size of that process, and okay, if it's too large and we're not obviously using a lot of heap, then means that we're actually having these allocated arenas for threads that are just there and not using the arenas that much. So maybe we want to play around with these parameters. And usually what you do is that you don't really touch the ncore, but you touch this one to kind of force it to a certain value regardless of the number of cores. So to give you an idea. Okay. Okay. So this is actually an interesting structure. It's called Heap Info. This is the arena information. Um, it points to an M state, which is basically, if you remember, we had this struct that would give us the state of a heap before. This is M state. Let's just look it up here. So struct, this is M state. Yeah, the M state is the type of the main arena, right? So this main arena here is of type memstate. So what is main arena? It is of type malloc state, and this malloc state is actually type deft to mstate here. Okay, and we can actually see what malloc state is. Struct malloc. We've talked about this in previous videos, but let's just take a look again to remind us. Malloc state. So you see it's got the lock, this guy, it's got some flags, the bins and fast bins and whatnot, right? And it also points to a next pointer. The next pointer here is the adjacent arena. So every arena points to the next arena, which in this case it's pointing to itself because it's the only arena in this application, because this application is a single threaded application. So there's no need to have multiple arenas. And then the next free is basically the next arena that is totally free. Not even a single allocation has been done there. And this is the number of threads attached to this arena, which is obviously 1. How much system memory is occupied by this arena, and the high watermark of the system memory that was ever occupied by this arena. And this is not memory that is allocated, it's just memory that it's taken from the kernel, and it's being used by glibc either as in free chunks or allocated chunks. So this is the M state. So so this struct heap info, it basically contains a pointer to like something like the main arena, but it's for that specific arena. Okay. Now it points to the previous arena, and it includes the size of that arena, and it has some sort of a padding as well. Okay. Now, how do we create these arenas? Let's go and see that. So there are some, in the meantime, let's just pay attention to this, that there are some nice helper macros that you can redefine or recreate in GDB to work when you're debugging the heap. So one of them is this macro that translates a pointer address to the actual number of the arena that is associated with it. Okay, to the actual heap info, to the arena that is associated to this pointer. And that's relatively easy to do because you just compare the pointer address to the beginning of the arena. What I'm going to do now is I'm going to basically run a benchmark and see the effect of arenas. But before that, I'm going to run my benchmark. That's a multi-threaded application, and I'm going to attach GDB to it and just inspect the different variables related to arenas. So the benchmark that I'm going to be using is a benchmark that is provided by glibc itself. Like if you go into glibc code, there will be actually bench, something like that. Bench tests. Yeah. So if you go into bench tests, there are a number of benchmarks. Now, what I'm interested in is only the malloc thread, bench malloc thread, which is gonna do which is gonna create a bunch of threads and gonna do many different mallocs and frees and random order, random sizes to kind of stress your heap, right? And then you can assess the performance of your heap. You can just, make these by running the make file, and you'll get the uh, uh, binary, and then you can run the binary. There's a README here as well. Tells you how to make the whole bench, how to clean it, and whatnot. Now, I've done this, right, somewhere else, and I'm just gonna, I've copied one of these benchmarks here, and then make the make file. So I'm just gonna say it's basically the same benchmark. It's this guy, right? I'm just gonna say bench malloc thread and just run 10 threads, and it's gonna run a test for 10. It's gonna create 10 threads, and the test is gonna be 1 minute. Okay. Now I'm gonna do this. I'm gonna open a window and say PID of bench malloc thread. So this is the PID. Now I'm going to run gdb. Well, actually, I need to be sudo because I'm attaching to a different process, sudo gdb. And I'm going to say attach to that PID. Okay, it attached. Let's get a backtrace here. Okay, if info threads, we have from thread 1 to thread 11, and I believe one of them is the main one that kind of then creates 10 other threads. So the main one waits for the whole benchmark to finish, and then it terminates the whole thing. So let's take a look at the main arena. Okay, I have my main arena, and see, there's a next here. Sorry. Yeah, there's a next, and this next is not pointing to the main arena, right? It's pointing somewhere else. See, these are the address of range for the main arena. This is main arena, right? This is totally different address. So it's a different arena. So if I say next, this is going to be my next arena. So what I'm going to do is I'm just going to print the contents of this guy, which is going to be my next arena, arena number 1, right? And I can see that, in this arena, I have some fast bins being occupied and whatever, different top chunk, and then these are the bins and whatnot, right? So in this arena, I have 1 thread attached to this arena, which is a good thing. I don't want to have too many threads for an arena because then you have to contend on the lock. And then this arena is using 192 kilobytes, and then the maximum ever used is also this one. And it also has a next pointer, which is different. Like the address range is different. The other ones had the mutex to 0. So there's a next, and we have 1 thread attached here. Again, same amount of memory used, and 8A something, but then this is 8B something. So this is a different range. Now let's also take a look at the proc 44138 maps. And this would be the memory map. And I just want to show you that you see that these mappings that are anonymous below the heap, these are all the separate arenas that are being created. If you remember, and from previous videos, we usually had this and that was it. Sorry, so we only had this part and that was it. Now we have a whole bunch of this. Well, it's not marked heap because the system only identifies the heap as the main arena, which is extended by break, right? These ones are disjoints from the heap. Look at the address, so it's not going to mark them as heap. But we know that they are the heap. And look at the address range here. A8000. And if I go here, see this range? That's it. This was the next pointer. Yeah. Here. There you go. So the next pointer of the previous arena is this one, and this pointer, pay attention, 80000, which is 8 all the way 0 to the end, right? That's the beginning. So these are actually the arenas that we have. Okay. And I can go through these arenas forever until I kind of circle back, because the last one is going to point to the main arena, right? So the main arena, we know that starts from 5, 6 something, right? Whenever we get back to that, we should realize it. Next. Oh, sorry. Yeah, not back yet. So the next is still going on, right? Still going on. I can do this forever. Just want to show you it kind of circles back. Not yet. It's gonna take forever. Yeah, so we're actually down to 38D, which is 38D. See here? 38D. Wow, we have a lot to go. Let's just give it a few more shots. Oh, actually, no, we're good. Yeah, there you go. We got to the main arena. That's it. Yep. So this last one, this is the main arena, and then one more. So arena 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the next of 10 points back to the main arena. So we have a main arena plus 10 more, which makes sense because we had 11 threads, if you remember, right? Say info threads, we had 11 threads, right? One was the main thread, 10 were the other one created for doing the malloc and whatnot. Okay. So I guess that kind of cleared things a little bit for you to see what the arena is, and and definitely you can go inside each arena and and inspect this more if you want. Let me see if I look at the top chunk. This is the top chunk of one of the arenas. Let's just dump the memory here. I just want to dump this. Okay. And this is the top chunk. If I go back a little bit, let's say I go back. Actually, you know what? Let's just do this much. Yeah, so these are the blocks of memory that we have, and I was actually hoping to find an allocated block of memory. So if I want to go to the beginning of this, okay, let's see now. Well, you know what? We have it here. So this guy starts from here, right? This address would be the beginning of one of the arenas. Okay. See what we have here. So that's the beginning of the arena. Okay. Um, Interesting to just take a look. And these are actually the bins. If you pay attention, these are actually the bins. Okay. And I can go on, and we can see these bins, right? These would be the bins. Okay. Anyways. So here, this is actually a block of memory. And pay attention to the 5 at the end of this block of memory. And let's see what this means. Let's go back to this. A block of memory has a metadata like that. Okay. AMP. A, it says if it came from the main arena, this bit should have been 0. It was all 0 all along throughout all the videos up to this point, which were only allocated from the main arena. Now this one has this bit as 1, right? Which means it's not from the main arena. So this is a way for us to know if a memory, if a block of memory is part of the main arena or is it part of one of the other arenas. We should look at the uh, third bit from the right, the LSB, right? 0, 1, 2, or 1, 2, 3, whatever, however you want to count it. If this is 0, it's from the main arena. If it's 1, it's from one of the arenas, right? This is obviously for directly mmap blocks, and this is for the prev in use, right? So that's also something to notice, which is interesting to see. And so that's the arena, right? What I want to do next is I want to assess the performance of having different number of arenas for a multi-threaded application. So let's just run this to completion and we'll actually quit. What I want to do, well, this test bench ran, this benchmark ran. What I'm going to do next is I want to run this, right? And then change glibc tunables so that I have more arenas, less arenas, and then see how it impacts the performance of this benchmark, because then I would have to acquire locks or not acquire locks. And okay, so what I'm going to do for the performance valuation of the arenas is that I'm going to run this bench malloc thread with 10 threads. But what I'm going to do is I'm gonna leave all the glibc tunable parameters as default, but I need to turn off the per thread cache because the T cache is also a further optimization for multi-threading when you want to kind of improve the performance of a multi-threaded application when it's using the heap. So I need to kind of disable this so that it doesn't interfere with the results of arenas. So we'll talk about Tcache in a different video after this one, but for now, let's just assume that we don't have Tcache. Okay, so I'm just going to run benchmark. I've ran these before. I've ran these before, and here are the results. It tells us that every malloc-free takes 120 CPU cycles. Okay, when there is no limitation on the number of arenas. Okay, now, well, there could be some fluctuation here, like if I run it another time, but for now, that's 120 CPU cycles. But what if I run it with glibc malloc arena max equal 1, which would set a maximum number of arenas to 1? Okay, and that means that it's only going to have the main arena, and that's it. In this case, as you can see, the CPU cycles per malloc free is 6,681. So that's almost 50 times the value. So the performance went down by 50, a factor of 50. That's a lot. So, just using as many arenas as threads is going to make our code 50 times faster. I mean, the allocations and free part of the code. But it turns out that malloc and free, actually heap, is frequently used. So it is very important to have a very high performance heap. Now, we saw the effect of having arenas on the time it takes to execute a malloc and free. But let's dig a little bit deeper. Now, obviously, if I, for instance, increase the number of threads, this is going to be even more um, significant, the difference. Now let's see, why is this? Well, we all know it's because of holding the lock. So I'm just going to do something interesting. I'm going to trace all the system calls as a result of running these commands. And I'm going to do that by running sudo perf trace -s, which is going to be the system calls. I will say syscalls. No, actually, -s means it will just give me a summary. Well, you know what? I'm just going to remove. Just going to say, okay, so I'm going to say sudo perf trace --syscalls. Oh, trace all the system calls. And I have to say env this guy. So this will be the environment variable. And there you go. I have to be sudo to be able to run perf. Well, you can see that it's got like some M maps, and because it's allocating these. If you remember these addresses, these were for the new arenas. So it allocates a bunch of arenas, right? Right at the beginning. These are the arenas. They're both read and write. And then we have a bunch of breaks here because it's extending the main arena. What else? It's protecting the memory as you go forward and use more and more of the heap, you protect it, meaning that you kind of make that part read and write, basically able to read and write in that part. Okay, so this is it. That's it. Not a lot of things going on. I mean, very interesting, but no locks acquired, no few tags. I'm just going to end this. Control C. What I'm going to do is I'm going to run this, but with arena set to 1, maximum arena set to 1. I'm just going to say sudo perf trace syscalls and well, tcache is disabled. I don't want it to interfere here. Arena max is 1, and here we go. Okay, sorry. My mistake. Env. I need an env here. Wow. A lot of system calls. And if you can pay attention, you see the futex, right? A lot of futex is being taken. I'm just going to stop it. Look. How many futexes do we have? And look at the time. And this, like, nothing. Right? Futex. Every couple of milliseconds, there's a futex system call, which is relatively heavy. Some of these would actually block the thread. Some of these would acquire the lock successfully. So for instance, this is the amount of time that took to execute this system call and return from it. 0.1 millisecond. Sorry, 0.001, like a thousandth of a millisecond, which is 1 microsecond. This was 13 microsecond. Maybe this one was when the lock was actually the thread was blocked. Maybe this one, these small ones, is when the lock is free and you can acquire it. So you can see that, yeah, you're spending a fair amount of time and running a fair number of these futexes just because you don't have the arenas, right? In this case, 20 microseconds, so on and so forth. And if I have more threads, let's say I have 20 threads, it's just going to make matters worse. Okay, take a look. There you go. We see very large waiting times, like the time it takes to execute this system call is just a lot, right? It's way more. So it just gets worse as I add to the number of threads. Now, if I increase the number of threads, let's say I just 5 threads, right? It's a lot better. Look at the times, right? Or if I go now, say 10 threads, right? It's much better. The delay is actually, yeah, here. See a lot of small delays and, large delays as well, but it gets a little bit better, right? So you get the idea. It's because of the few text system calls. Now I've already ran this using the -s parameter, which only provides you with a summary. So it doesn't print every system call. Like you go -s, it's going to give you a summary. And I'm going to share those results with you. And let's see. Okay. So this is for when Tcache is off. Fast bins are off. Well, they can be on or off. Doesn't really matter. And then we have 1 arena, 10 threads, 5 arenas, 10 threads. Okay. So let's look at this guy, which is probably the worst case because we only have 1 arena and 10 threads. Like if you take a look at these, so this is the summary of all the system calls. This is the main thread. I wouldn't really look at this one because this doesn't do a lot of mallocs. But then the rest of the threads, they're the ones that do the mallocs. So you see, it's being governed by, dominated by few text and break, obviously, and yeah, well, some other ones which happen rarely. So let's say 370 breaks, but look at this few texts, 6 million, 6.4 million few texts. And then the total time is you're spending 40 seconds inside the few text. So 40 seconds, that's a lot of time. And on average, 6 microseconds is spent in a few text. The maximum is 57 milliseconds. You see, it's a lot. Like in total, this one thread only wasted 40 seconds inside few texts. And it's pretty much the same for the rest of the threads as well. If you just take a look, the average and everything. So have these numbers in mind, especially the average waiting time in a few texts, which is 6 microseconds. I'm going to increase, let's see the result for when we have 5 arenas. Obviously, when we have all the arenas, we're not going to call the few texts, so I'm not going to show that, right? We already know. But this one, I have half arenas as threads. And already you see like 6.4 million calls to few text come down to 4.6 million calls to threads and to few text, which is the lock. And from 40-second wasting time in few text for this thread, I'm now down at 13-second, 12-second, which is a lot. And then the average time spent in a few text is cut in half, right? So although the max is still pretty much the same, because you could still have a worst case contention where a lot of these threads want the same arena at the same time. So the max is still there, but the average has been cut down really. So this tells us the effect, the significant effect of arenas on the performance of multi-threaded applications. Okay. The only downside to having arenas is that you're going to have more memory mapped into the virtual address space, and you're going to have like a larger residence set size, which is the RSS size. So like if you do top, for instance, well, actually you have it here. We should have it somewhere. Okay, when we ran these tests before without, yeah, okay. So when we ran these tests before, like I'm just going to say top, and then this bench malloc, right? The RSS here, that's the resident memory. So that's in kilobytes, 1.7 megabytes. That's when I have all the arenas. Now, if I just wait this for this to finish, and then run another instance of it. So the max RSS, max resident is this much. I'm going to run this with arenas limited to 1. Yeah, okay. So here we have arenas limited to 1, and I'm going to run this. Okay, so you can see here that the maximum resonance size here, where you have all the arenas, is 3.4K meg, and in this case it's 2.7K, where you have limited the number of arenas. So obviously if you have more arenas, you're probably going to have, like, at least the peak size is going to be more. Okay, I hope you've enjoyed this video. In my next video I'll be talking about the final piece of glibc, which will be the per thread cache. And I hope you have enjoyed this one, and I hope you'll watch the other one. Thank you very much. Hit the subscribe button if you like this, and don't forget to leave comments if you wish.